Okay, so here's where we left off on the last video. All right, and we look at the scope, and we're basically comparing versus the command signal, and we see that we're perfect. All right. So I think it's pretty useful to kind of look and see, what's the inverse dynamics doing, and what's the PID doing. And so we're going to take those two components and show them in the same scope here. So let's rerun that simulation. So basically, how much torque is delivered by the PID algorithm, and how much is delivered by the inverse dynamics. Okay, and let's do that, and let's zoom in to where all the actions are occurring. All right, and the PID, that's going in the first port, so that's why it's yellow. It's like it holds on to 0 throughout, and so we look at something like this, and it almost looks like the inverse dynamics is doing everything, right? But it's useful to look at each of these scopes through their own display, all right? And so let's do this, all right? And certainly if you consider the magnitude of the inverse dynamics, it's operating, I don't know what that is, maybe 550 Newton meters compared to something close to 0.05 on the PID. That might make you think it's doing everything. But I think these little oscillations are real important. I think that the big oscillations that are occurring, as the ramp begins and the ramp completes, that this is really telling the story of PID and what it does really, really well. Okay, and here's what I want you to imagine. First of all, let's think of like the inverse. Well, yeah, the inverted, not the inverse, the inverted pendulum. The control of it's the fact that as soon as it begins to sway a little bit, there's going to be some sort of force that'll be kind of nudging it in the other direction. And so there's this kind of rapid control. And that's really kind of what we're seeing here. And as we bring that beam up to 45 degrees, and even as we hold 45 degrees, there is a tendency to drift. And because we have a immediate measurement that's being fed back immediately to the PID has the ability to rapidly, kind of address that drift and restore it to the angle that we wanted it at. So that's the basic idea, and why PIDs are so good. Or there's lots of things to talk about PIDs, but certainly that's an aspect of it that really helps us keep this thing stable. All right. Now I want to explore that point a little bit more clearly because we haven't done this simulation yet. Let's comment out the PID, and let's run it again. So it looks pretty good. Oh, yeah, look at that. So that's that stability issue. And it takes a little bit of time for it to get started, but boy, it goes crazy without the PID. All right, so what I want to now kind of consider is, well, what do we even need inverse dynamics for? That trick of just making the PID stronger and stronger, maybe we should just continue to go with that. So let's comment that out. Let's bring this one back. All right, and this is going to be a simulation that we've already seen, but it's kind of a good starting point for what we're about to do. Okay, so with purely PID, maybe you saw it, there's a little bit of an overshoot there. We look at the scope, and we see that overshoot almost hitting 50, so compared to 45, about 4 or 5 degrees of overshoot. And so the idea is, let's go back here, let's look at these values, and let's update them one more time with a little bit faster. And we see better, rise time, settling time, and so forth. So let's update the controller with that. And let's run it one more time. All right. And so absolutely, It looks very good. All right, we see a little bit of oscillation there, but it looks like on the order of less than a tenth of a degree. Okay, so anyways, why don't we just use PIDs for everything? And, all that seemed pretty simple. And so it really kind of gets into implementation that, this is a mathematical calculation. It's a formulation that gets run on a computer, an embedded processor computer that is integrated into your equipment. All right. And like any computer, I want to show this. All right. At least this kind of, I think it means something to a lot of people. The S stands for what they call that S variable in Laplace transforms. Right. And so Laplace transforms is sort of like the continuous functional representation of this, all right? And in a way, that's cheating. That's infinite, sampling, meaning I always have immediate information about where that, angle is for the pendulum, all right? And so you do this. This will be a little bit unfair, but let's go ahead and do it this way at first. All right, I'm going to put in a reasonable sampling time of 0.001. Right. Right. So this is a discrete calculation now. Okay. So obviously crazy unstable. Right. So what do we get to there? Yeah. 10 to the 150. That's really unstable. All right, so as I said, what I did was a little bit unfair. It's not really a fairness thing, but it's as soon as you make that discrete change, it's a good idea to retune the controller. So we're going to reset all those values. And if our sampling time, where we put in 0.001, if we make that really, really small, the discrete controller should be pretty much the same thing. Let's see, do I have it? Okay, I don't understand this, so let's just redo it. I think it's because it's already open, it gave me kind of a weird result, so I want to tune it again. Okay. So these are, that conservative, auto-tuning algorithm. It's conservative because there's a faster button that allows you to interact and make it stronger. We got these really small values again. So I'm going to just, right off the bat, get it to where we were before. I like kind of this image because it's really getting at what we really mean by discrete, which is, at each point in time where we sample, and sample is make measurements of angles, but also assert the new torque, that the torque being received kind of looks like this. It's kind of got the staircase kind of nature to it. And let's see, notice this. I can't even click on it anymore. And so these values are probably about 10% of where we were. So let's go for it. But what we're seeing here is a constraint imposed by our tuner is saying this is the best you can do because it knows it's unstable if we go past that. So let's update those values. See, those are in there now. Let's click on OK. And my PID tuner said it would be stable, so let's see how it does. Okay, and so that looks pretty good, but the best it can do, is going to give us an overshoot about 1 degree. And I can just speak for some of my customers. 1 degree of error on angle sounds small, is enormous for them, right? And so bringing back the inverse dynamics, we see, I believe we'll fix this, but that's what the run button's for. Let's find out. Looks real good. And we got rid of that 1 degree overshoot. So we zoom in real close. That's way, way smaller than 1 degree overshoot. So inverse dynamics is really helping us there. I think the last thing I want to do on this one is that with inverse dynamics, we don't need that PID to be super, super strong and quite so active. And so what I want to finish on is let's reduce that sample rate to 100 hertz. Okay, we've already proven that we need a PID, but maybe we don't need a super active one. My error. Okay, the PID needs to be retuned again, of course, right? So I'd say anytime you reset that sample time, retune it. Show those parameters. And that's as fast as it will go this time. But PID tuner is telling me it will be stable, right? So let's update the block. There's the new values. There we go. All right. And that last bit of going from 1,000 hertz, and even 1,000 hertz can be a little bit slow for motor control, or the way that they'll control these things. I think we're showing that at 0.01, I probably can do that with my Arduino, which I love Arduinos, but they're kind of designed for fun and ease of use. But they usually operate at a much slower sample rate, right? And so, anyway, with all due respect to Arduino, that I can, and here's the main point. Again, they're for fun and they're very educational, and that's why they sell them at about probably $35 or $40. So I can do this very inexpensively because I am using this inverse dynamics to supplement the controller and allow the PID to operate at a reasonable rate and do the thing it's really good at, which is attending to the stability of the system. Thanks for watching.